Okay. So, just before taking few examples, let us summarize about for series capacitors, right, what we have studied before taking the example, right. You will find some interesting things. A series capacitor, when you do, that is your power loss, that is without your what you call with series capacitor divided by power loss, right, without series capacitor. This actually it is inversely proportional to the square of the voltage magnitude. So, we got this one V square upon V c square, right, this one we got. So, just for the purpose of this thing, suppose before capacitor, this is V is that without capacitor, that is why writing V. Suppose it was 0.95, right, and suppose after placing capacitor you got 1.0. This is just an understanding, that means P loss with series capacitor will be, it is V is equal to 0.95 square, voltage has improved because of capacitor is 1 into your P loss without series capacitor, because it is inversely proportional. So, naturally 0.95 square whatever will come, right. So, that much of it is without series capacitor, right, and with series capacitor 0.95 square whatever it will come, right. So, multiplied by this thing, that means with series capacitor power loss actually, although not much, but to some extent it actually power loss, it reduces the power loss. This is a simple example I am giving, and that is why we have got this formula P loss without S C by P loss with S C by without S C is this much, right, because it improves the voltage level. This is for series capacitor. Just and for the shunt capacitor, what we got? We got for shunt capacitor, right, shunt capacitor, right, what we got, that without anything, if current is say I equal to I d minus j I q, then its magnitude I is equal to root over I d square plus I q square, right. That means this one is equal to I d square plus I q square, right, and power loss, say real power loss multiplied by R. So, R I square, right, is equal to R into I d square plus R I q square is equal to your R I d square plus R I q square. This part we are calling, if you call it as a, this part is a d axis component, say this part is P d and this part is P q, right. So, this way if you made, right. So, and if you put the shunt capacitor, then at that time current is coming I d minus j I q minus I c, right. Therefore, magnitude of this one I dash square is, take magnitude then square, it will be your I d square plus I q minus I c whole square, right. So, its power loss will be then R I d square is R I dash square is equal to R I d square plus R I q minus I c square whole square, right. So, that means it reduces the power loss, it directly it, or what you call it directly, or what you call reduces the reactive component of the current. So, this part I told you I q, if you made I q is equal to I c, then your what you call this this part will remain same, this may be 0, but this part will almost unchanged. This is the inherent property of any circuit, this cannot be made to 0, right. So, this loss will remain in the circuit whether it is direct axis. Similarly, if you multiply by x, so x into I d square also will remain in the system, that is the reactive component, right. But this part if you make it vanish, that x into plus x into I q minus I c square. So, this is one thing. Another thing is that shunt capacitor, though not much, it improves the voltage magnitude level. Therefore, same philosophy, that is P loss, right, with writing full form with that SH is shunt capacitor, then P loss, that without shunt capacitor is inversely proportional, loss is inversely proportional to the square of the voltage magnitude. So, this one can be made as, suppose it is V 0 magnitude, that is without voltage without shunt capacitor, and this is say your V S H, that is with your what you call shunt capacitor, because of shunt capacitor voltage has improved, and this is your V 0, right. For example, if say V0 is equal to say 0.95 and suppose your VSH, suppose due to your shunt capacitor, suppose voltage has improved to 0.97, right. Therefore, 0.95 square by 0.97 square, it will be less than 1, right. That means P loss is less than 1 means some point something will come, 0.9 something will come, say, right. So, in that case, that due to shunt capacitor also voltage your power loss also reduced to some extent, right, because this term will be your what you call less than 1. But if you some cases in distribution system, if there are some nodes, it may happen that it is a large network, of course, some nodes it may happen that sending and receiving end voltage is slightly greater than sending end voltage. This may also happen, but that is maybe a large network, maybe 2-3 nodes it may happen, right. But otherwise that shunt capacitor also improves the your voltage level. So, it also reduces the losses, but not like series capacitor, because series capacitor case this voltage rise is very high, right. So, these are some general ideas for series and shunt capacitor, right, that how things are. Now, let us take the example. So, assume that a 700 kVA load has a 65% power factor, is cos phi cos theta is equal to 0.65. It is desired to improve the power factor to 0.92, that is 92% means 0.92. Determine the following: the capacitor size required, what will be the resulting power factor if the next higher standard capacitor size is used. Actually, in market, if you ask for give you a capacitor of 337 kilowatt or 23 kilowatt or 405 kilowatt, it is not available. Some standard ratings of capacitors are available in the market, like 25 kVAr, 50 kVAr, 65 kilowatt, then 100 kilowatt, 200 kilowatt, like that. If you take a 75 kilowatt also sometimes available, but if it is not available, then perhaps you have to use 125 kilowatt, 150 kilowatt bank, right. So, this is a combination. So, that is 700 kVA load is there, 0.65, power factor to be improved to 90%, 92%. So, 0.92. So, you have to determine the capacitor size required and what will be the resulting power factor is the next standard. I mean, whatever capacitor size is required means, suppose you have got some value say 331, but this is not available. So, nearest rating will be either 325 you take or 350 you take, but 331 cannot. Accordingly, you have to see how your things are, and if with that new size you find out what is the power factor, right. So, in that case S is given 700 kVA, it is 700 kVA, initial power factor is given cos theta 1 0.65. So, P is equal to your apparent power into cos theta 1. So, S cos theta 1 is equal to 700 into 0.65 is equal to 455 kilowatt, right. So, cos theta 2 is equal to say improved power factor is 0.92. From equation 9 we get cos theta 2 is equal to P upon root over P square plus QL minus QC whole square. It is putting half actually root over. So, that is actually P is 455 and this is 455 square plus QL minus QC square, this is half, right. So, QL will become after, because cos theta is your what you call theta 1 is 0.65. So, substituting all this you will get QL is equal to 532 kilowatt. This here this is your load reactive power, right. This QL is 532 kilowatt load reactive power. Now, second case your what you call this is given, QL is equal to given. Now, you put in this equation that you want to improve power factor to your 0.92. So, cos theta here it is 0.92, P is remains same 455. So, 455 upon 455 square plus 532 minus QC square to the power half, right. So, in that case your what you call this one, that then square it both side. So, 455 square plus 532 minus QC square is equal to 455 upon 0.92 whole square. So, it will get 532 minus QC plus minus 193.83. So, QC will be just changing the sign, 532 minus plus 193.83, or you will have two values, QC will be 338 or QC will be 726 kilowatt, right. But your what you call your load, this QL is equal to 532 kilowatt, right. So, if QC becomes your what you call 726, it is more than your what you call that QL is 532 or something, right. So, it will operate leading power factor. There is a possibility that then in that case that your receiving end voltage will be higher than the sending end voltage, right. But anyway, we will take the lower one. So, that is QC is equal to 338 kilowatt. This is that the point power factor is maintained 0.92, right, but 338 kilowatt capacitor size is not available in the market. So, standard capacitor size may be QC is equal to 350 kilowatt. It is actually capacitors are available in bank like 25 kilowatt, 50 kilowatt, then 100 kilowatt, then your 200 kilowatt, like that. So, some combination you have to take. A single bank of 350 kilowatt may be available, may not be available, right, but some combination. So, standard capacitor will be 350 kilowatt, right. In that case, new power factor will be same formula that cos theta 2, that equation 9, P upon root over P square plus QL minus QC whole square to the power half, but QC you should take your 350 instead of you got 338, that is why you got 0.92, but you take your 350. So, if you take 350, then cos theta nu will be 450 upon 455 square plus 532 minus 350 whole square to the power half. So, it is 0.9284. There is slight improvement of the power factor, right. So, this is your QC. Now, another thing is another formula called computing QC is equal to P tan theta 1 minus P tan theta 2. Then again I have to go to that power triangle, right. How we are getting P tan theta 1 minus P tan theta 2. First let me go to that power triangle, right, whatever we have made it. This is your power triangle, this is your power triangle, this QC you have to make it, this QC you have to make it, right. So, what will be QC? Initial power factor was theta 1, right. So, Q is QC or initial, that means let me write down here. So, initial power factor was theta 1, this theta 1, therefore, say I am making something, say your Q or QL, Q is equal to QL is equal to P tan theta 1, right. Then new power factor is your theta 2, right, that means this much your what you call this PD, this your PB this much, P to B this much. So, suppose this is Q is equal to P tan theta 1 and say PB say is equal to Q dash, that means this PB Q dash is equal to your P tan theta 2 is equal to P tan theta 2, but this is actually QC from here to here, that AB actually is equal to QC in this diagram. Therefore, AB is equal to your this one your AP, this is actually your AP, this AP minus PB. So, AP is equal to your P tan theta 1 minus P tan theta 2 is equal to P, then tan theta 1 minus tan theta 2, that is actually this is actually QC, this is actually QC. Therefore, this is actually QC is equal to P tan theta 1 minus P tan theta 2. So, that is why your here in this equation we are writing or QC is equal to P tan theta 1 minus P tan theta 2, or tan theta 1 is equal to that tangent of the original power factor angle and tan theta 2 is equal to tangent of the improved power factor angle. I mean using that other formula also, apart from that one, this one also you can use, right. So, cos theta 1 is 0.65. So, theta 1 is 49.45 degree, cos theta 2 is 0.92. So, theta 2 is 23.07 degree. So, if you take tan theta 1, that is tan 49.45 degree, it is 1.1687 and tan theta 2 is equal to 0.4259. So, you substitute here P is 450 kilowatt, that is given. So, QC is equal to 455 your into tan theta 1 is 1.1687 minus 0.4259 is equal to 338 kilowatt, same as we have got earlier also, right. So, this is the way that you can calculate QC, but nearest side is 350. So, that is why 350 we have used, but this is another way of computing QC. Now, I take another example. Assume that a 3-phase 500 horsepower HP motor operating at 60 hertz and its voltage is 4160 volt, that is 4.16 kV, right. Star connected induction motor has a full load efficiency of 88%, 0.88 is its efficiency, and a lagging power factor of 0.75. So, it is a poor power factor, right, and is connected to a feeder. If it is desired to correct the power factor of the load to a lagging power factor of 0.9 by connecting 3 capacitors at the load, right, determine the following: the rating of the capacitor bank, the capacitance of each unit if the capacitors are connected either in delta or in star, right. These are the two things you have to do it. So, first is the induction motor of the what you call input power of the induction motor efficiency is given 0.88 and 1 horsepower is equal to 0.7457 kilowatt. So, how we are writing P is equal to 500 horsepower and it is 7.71 horsepower is equal to 0.7457 kilowatt. So, we are writing 0.7457 kilowatt per horsepower divided by efficiency 0.88, that actually 423.69 kilowatt, right. So, the reactive power of the motor at the uncorrected power factor, just now we have seen that Q is equal to Q L is equal to P tan theta 1, right. So, it is equal to 432.69, cos theta is equal to given cos theta 1 is equal to given 0.75, therefore, theta 1 is equal to cos inverse 0.75, directly we are writing, it is understandable to you. So, cos inverse actually tan of cos inverse 0.75, right. So, this is actually coming 373.7 kilowatt, that is QL. Now, the reactive power of the motor at the corrected power factor, now corrected power factor is 0.9. So, cos theta to 0.9, therefore, your theta 2 is equal to cos inverse 0.9. So, that is why this your what you call twice I have written tan, it is actually 432.69 tan of your cos inverse 0.9, right, whatever angle it comes. So, Q will become 205.2 kilowatt, this is your second case. Then what is the QC? Then you have to subtract that one, what will be the value of QC, right. So, this is your total Q and this is your after power factor improvement. So, subtract this one from this one, that will give you QC value. So, in that case, that is your QL minus QC, that is your QC, that means your this is QL minus QC. So, this is whatever you have got QL minus QC. So, QL minus QC is equal to 205.2. So, QC is equal to your this one minus this one, same thing, right. You subtract this one from this one, right. So, you will get QC is equal to 168.5 kilowatt. This is the capacitor you require. Now, hence assume the losses in the capacitors are negligible. Suppose there is no loss in the capacitor, therefore, the rating of the capacitor bank will be 168.5 kilowatt. Now, if the capacitors that it is given, you find out the value of capacitance C if the capacitor either it is delta connected or it is star connected, right. So, this is the 3 phase line A, B, C phase, right. So, we are taking the capacitors are delta connected first. So, this is IC, the capacitive current, and this is the line current IL, balance system. So, all are same, right. So, figure number I have not given here, if the capacitors are connected in delta and shown in figure, actually this is the figure, no number is required here, it is numerical. So, this is the figure, right. So, you know that is 3 phase 1. So, your root 3 V line to line voltage into IL, the load current, is equal to QC. Therefore, IL is equal to QC upon root 3 into V line to line voltage, we are writing directly. So, QC is equal to, it is 168.5 and line to line voltage, it is root 3 into V, it is line to line voltage is given in the numerical, that is your this value, that is 4160 voltage, that is your 4160 volt. So, it is actually 4.16 kV divided by 1000, right. So, because QC is we are taking at a kilowatt, so voltage we are taking at actually kilovolt. So, naturally I will be in terms of it will be in current ampere, right, 23.41 ampere. This is the your what you call the load current, right, and it is a balance system, the magnitude of the current. Now, therefore, that IC is equal to IL by root 3, because this is a load current and this is a delta connection. So, your phase current will be your what you call line current by root 3, right. That means, IC will be IL upon root 3. So, in that case IC is equal to IL upon root 3. So, that is your 23.41 upon root, that is 13.53 ampere, that is IC, right. That means, this is the current flowing through the capacitor, this is the current, right. Therefore, Xc, the reactance of each capacitor, we can write Xc is equal to, you can write VLL upon IC, right. So, in that case, whatever value you will get, right. So, this is a delta connection. So, why line to line voltage, this point means this point, this point means this point. So, line to line voltage actually impress acts as the capacitor, because this point same, this point same. So, just take one example. So, the line to line voltage is impressed across the capacitor. That is why we are taking X is equal to V line to line upon IC. So, that is actually, now we are putting it, IC is ampere, we are putting this one as a volt, then we will get the ohm. So, 4160 instead of kV, 4160 volt by 13.53 ampere. So, it is coming 307.38 ohm, right. And we know that Xc is equal to magnitude, of course, 1 upon omega c, and this one is equal to 307.38. If you solve this one, omega is equal to f is 60 hertz, so 2 pi f, and c is equal to 1 upon omega into Xc. So, 307.38, you will get 517.78 microfarad, the c value. That means, this capacitance value is a microfarad, right. So, now if it is a star connected, then IL is equal to IC. If it is star connected, one I am showing in every phase that IL is equal to IC. I forgot to mention it here, that is why I am writing IL is equal to IC. It is a star connected, right. So, in that case, if the capacitors are star connected, then IC is equal to IL is equal to 23.41 ampere, right. In that case, you have to take the line to neutral voltage, because it is a star connected, right. So, in that case, it will be your V line to neutral is equal to 4160 by root 3, and IC is equal to 23.41 ampere, right. So, Xc will get 102.72 ohm. So, again Xc is equal to 1 upon omega c is 102.72, and it is 60 hertz system. So, C will become 25.82 microfarad, right. So, this is that problem. So, it is not difficult one, easy one, but if it is star connected and if it is delta connected, whatever it is, that var has to be same, right. Capacitance C value different, but rating has to be same, and it is your choice whether you will go for a delta or star connection. But let me tell you one thing, their question to you, whether under such condition, whether we will prefer delta connection or star connection of this capacitor. I have taken delta and star both, but this is a question to you, delta or star. Please, I mean, when you will listen to this video, please you tell me the reason in writing few points, right, which one you will prefer and which one will be better, either delta or star, right. Think and then you will answer. Don't try to write quickly, you have to think and you have to answer, right. Now, example 3, assume that a 2.4 kilovolt single phase circuit feeds a load of 360 kilowatt and lagging power, and at a lagging load power factor, and the load current is 200 ampere, right. If it is desired to improve the power factor, determine the following, right. So, the uncorrected power factor and reactive load, the new corrected power factor after installing a shunt capacitor bank with a rating of 300 kilowatt. This 300 kilowatt shunt capacitor bank is mentioned. So, you have to find out all this, right. So, in this case, that solution part A, right. Before the power factor correction, right, that S1 is equal to V into I, the apparent power VI, you know as this thing. So, 2.4 kV is the voltage and current is 200 ampere. So, it will become 480 kVA, right. So, therefore, the uncorrected power factor cos theta will be P upon S1. This P actually given 360 kilowatt, this is given, this is given. Therefore, it is 360 upon 480. So, 0.75, right, power factor by 4 power factor 0.75, right. So, now and the reactive load is that S1 is equal to that cos theta 1 is 0.75. So, theta 1 is cos inverse theta 1. So, you can calculate easily, instead of calculating directly I am writing S1 into sine of cos inverse theta 1, right. So, QL is equal to S1 is 480 and this part will be 0.661, that is 317.5 kilowatt, that is your reactive load demanded at the your load, right. Now, after the installation of 300 kilowatt capacitor, effective Q will be QL minus QC. So, 307.5 minus 300, so it is just 17.5 kilovar. So, from equation 9 you know that cos theta 2 the new power factor, right, after placing the shunt capacitor, that P is equal to P square plus QL minus QC whole square to the power half, right. So, that is P is equal to 360 divided by 360 square, and this is QL minus QC 17.5 square. So, power factor is nearly unity 0.9989 cos theta 2, right. So, next one is another example, right. So, assume that a substation has a bank of 3 2000 kVA transformers, right, and that supplies a peak load of 7800 your what you call kVA, right. So, at lagging power factor of 0.89, so it is a good power factor. All 3 transformers have a thermal capability of 20% of the nameplate rating. That is that whenever they gave this kind of thing, that 120% of the thermal rating, thermal capability, that means you will consider this way, that I am sure that you have studied in machine design also for transformer design. The meaning is you take it other way, this transformer can take overload of 20% more than that, right. So, when it language will be something like this, the thermal capability 120, it thinks about from the temperature rise point of view and the insulation failure also, right. So, that means the transformer can take a maximum of 20% of the overload, that is all, that is the meaning. It has already been planned to install 1000 kilovar of shunt capacitors on the feeder to improve the voltage regulation. That means that your what you call that Vs minus Vr will improve. That means you are trying to improve the transformer voltage your regulation. I can say that you know that whatever voltage regulation you have studied for the transformer, right. So, determine A whether or not to install additional capacitors on the feeder to decrease the load to the thermal capability of the transformer or the rating of the additional capacitor, right. But whether or not to install additional capacitor on the feeder, whether that additional capacitor will install to the feeder such that to decrease the load to the thermal capability of the transformer, this is the meaning, and the rating of the additional capacitor. If so, then what will be the rating of the additional your capacitor, right. So, in this case, so before the installation of the 1000 kilovar capacitors, P is equal to S1 cos theta, it is given 7800 kVA into 0.89, it is given here, I have written here, P is equal to 6942 kilowatt. Therefore, QL will be S1 sin theta. So, cos theta is 0.89, so sin theta will become 0.456. So, 7800 into 0.456, it is 3556.8 kilowatt. Therefore, after the installation of the 1000 kilowatt capacitor, Q will be QL minus QC. So, this is your QL, this much of the reactive load, reactive power required in the load. So, Q should be equal to QL minus QC, that is your this much minus 1000, it is 2556.8 kilovar, right. From equation 9, we know that cos theta is equal to P upon P square plus QL minus QC whole square to the power half. So, P is given 6942, it is 6942 upon 6942 square, and QL minus QC is 2556.8. So, 2556.8 square to the power half. So, 0.938. So, power factor in the second case initially is 0.89. Now, power factor has improved because of this 1000 kilowatt capacitor. This power factor has improved, right. So, therefore, and the corrected apparent power is S2 is equal to P upon cos theta 2. Therefore, 6942 upon 0.938. So, 7397.9 kVA, right. So, that means corrected apparent power is 7397.97 kVA. Therefore, on the other hand, the transformer capability is, because there are 3 2000 kVA transformer. So, it is actually 2000 into 3 and the overloading capability is 1.2. So, it is 7200 kVA, right. But here it is 3097.9 kVA. Therefore, the capacitor installed to improve the voltage regulation are not adequate, right, because this is less than this one. Therefore, additional capacitor insulation is required. Thank you. We will be back.